I hope you all will enjoy having the Thursday off. I'm going to just go through quickly the main examples from section 8.1. The homework assignment on this section is labeled 8.1 and 8.2, so only the first 10 questions are from 8.1. So I'll put in my email that I would really like for you to try doing the first 10 problems from section 8.1, the first 10 problems from that homework set, which are the ones from 8.1. And just to make it easier, 5 of those same 10 problems are the ones that I'm going to show you examples of here. The main thing is that we're introducing what we call sequence notation, which is this thing using the little curly brackets. And what a sequence is a list of numbers that are indexed. So when we see this compact notation, what we really mean is a list that goes A1, A2, A3, A4, and so on. So the notation here, A sub n, is a little bit confusing because it has 2 letters in it, but the A part is just the name of the sequence, much the same way that when we say f of x, f is the name of the function, and x is a variable that we can change into a value. The same thing here, A sub n is a sequence, A is its name, and n is a variable that can be changed into a value. The catch is that the n's can only be whole numbers. So when we write A sub 1, A sub 2, A sub 3, A sub 4, we can think of the subscript as telling us which term it is. So A sub 4 means the 4th term. A sub 3 means the 3rd term. So we have a list which has subscripts, and the subscript tells us the position of the term. So, for example, in this formula, it's telling us, again, here n is the variable, and so if I change the n into being a 1, and I have to do it on both sides, it'll say 1 over 6 to the 1 plus 1, which is 1 over 6 squared, which is 1 over 36. So that's the correct value of A1. A sub 2 is 1 over 6 to the 2 plus 1. Again, back in this expression, I'm changing the n's, both of the n's, to 2's. That's 1 over 6 cubed, which is 1 over 216. A sub 3 is 1 over 6 to the 3 plus 1, which is 1 over 6 to the 4th, which is 1 over, oh, God help me, what is that, 1296? And I'll write and so on because I have no idea what 6 to the 5th power is. But this is the way that we can evaluate the function when we're given a formula in terms of n. Another way that a sequence can be described is it can be described as a sequence of partial sums. So what this means, we have a sum here, and it says in the sum that k goes from 1 to infinity, meaning that I would be adding up numbers forever. So first of all, let's think about how we read the sigma notation. When we see sigma notation, one way we can think about this is we can think, first of all, what are the possible values of k? And I can list them down here. The values of k, this notation tells me that the k starts with 1 and keeps going to infinity. But the k's have to be whole numbers. So k can be 1 or 2 or 3 or 4 or 5 and so on. So these are values of k. For each of those values of k, I can plug that value of k into this formula. So when k equals 1, I'll have 1 over 1 plus 2. So the 1 here is being plugged in for k in this expression. When k is 2, now the 2 is going to be plugged in for k. So when k is 2, I'll have 1 over 2 plus 2. When k is 3, I'll have 1 over 3 plus 2. When k is 4, I'll have 1 over 4 plus 2. When k is 5, I'll have 1 over 5 plus 2, and so on. The sigma, remember, the sigma means to sum the answers up. So when we write the sum from k to infinity, we mean take all of these terms and add them together. So this is what this is what the infinite sum, k equals 1 to infinity, would look like going on forever. Now the sequence of partial sums is just to build this sum one term at a time. So if I were to just take the first term, I would have 1 over 1 plus 2. If I take the first two terms, well, looking ahead of myself. If I take the sum of the first two terms, it'll be these two guys. The first three terms and the first four terms and so you can see that what we're doing here is, instead of this infinite sum, we're going to take just the first number, some of the first two numbers, some of the first three numbers, some of the first four numbers, and so on. So in other words, we're going to let this sum get larger and larger and larger one stage at a time. Now each of these for the homework set will have to be simplified. So this is a third, this is a third plus a fourth, which you'll have to simplify. It's equal to 7/12. This is a third plus a fourth plus a fifth. But notice that a third plus a fourth we've already done in the line before, and so this is really just adding one more thing on. And the same thing here. Once we've done the answer to the previous one, then this much will be from the previous one. So as you go, the partial sums are easy to do, because in each case you're just taking the previous partial sum and adding on one more term. The third way we talk about forming a sequence is using a recurrence relation. A recurrence relation is just a way of relating a term in the sequence to the previous terms in the sequence. To make sense of it, we are still using the idea that the formula can be interpreted by plugging in numbers for the ends. So for example, the formula in the box, if you think about what that says when n equals 1, it says a sub 1 plus 1, that's a sub 2, is equal to 1 times a sub 1. What I've done there, at least what I've tried to do, is to get this equation, I've taken exactly what's in the box and I've changed all of the n's to 1s. So here, if this n is a 1, then this is really a sub 2. This n is a 1, this n is a 1. So I've literally written it down like that. The reason that helps us is because we're given that a sub 1 equals 7. And so that means a sub 2 is just 1 times 7, which is 7. So I was given that a sub 1 was 1, and I was able to figure out that a sub 2, I was given that a sub 1 equals 7, and I can use that to figure out that a sub 2 is also equal to 7. So let's do it again. Now, use n equals 2 in this same equation. So again, writing down this thing in the box exactly, but changing all the n's to 2's. It'll say a sub 3, because on the left side it's n plus 1, a sub 3 is n, which is 2, times a sub n, so a sub 2. So again, you can stop and look. This equation and this equation match exactly if in this one you change all the n's to be 2's. This helps us evaluate the function because I know that a sub 2 is equal to 7. So 2 times a sub 2 is the same as 2 times 7, which is 14. If n equals 3, I'll have a sub 4 is equal to 3 times a sub 3, which is 3 times 14. The 3 is from here. The 14 is because a sub 3 is equal to 14 from the previous row, and that's 42. And then finally, when n is 4, this will say a sub 5 is 4 times a sub 4, which is 4 times 42, which is 192. No, it's not. 42, 84, 168. And so the first 5 terms of my sequence, remember I was given that a sub 1 was 7. So here are my first 5 terms. First term is 7, second term is 7, third term is 14, fourth term is 42, fifth term is 168. Probably the most challenging problem in these kinds of exercises are ones where you have to come up with a formula yourself, and so there's only a couple of those, and it's not essential for the calculus for our calculus purposes, but we might as well talk about it in a few simple cases. The first thing is to sort of spot a pattern, and if you're able to see the pattern or powers of 6 like I did in the previous problem, you'll notice that the pattern here is that, well, first of all, the numerator is always 5, and secondly, the denominator is a power of 6. So 6 to some power. I'll put a question mark. But that's what that looks like. So the next term of the sequence would be 5 over the next power of 6. This is 6 to the 4th, if you recall from the previous problem. So 6 to the 4th. So 5 over 6 to the 5th, 5 over 6 to the 6th. Those will be your next couple of terms. And so if I write down what I'm observing there, it's that A1 is 5, A2 is 5 over 6 to the 1, A3 is 5 over 6 squared, A4 is 5 over 6 cubed, and what I just figured out was that, oh no, I got one more, A5, A5 is 5 over 6 to the 4th, so those are all the given ones. And then I think that the next two are going to be 5 over 6 to the 5th and 5 over 6 to the 6th, but I have to figure out what those numbers are. So from one to the next, well, first of all, let's look at the explicit formula. Because I can write it in a common form, all I have to do is see what is the connection between the subscript and the exponent. The only thing that's changing as I go from one to these to the other is the subscript changes. So I'm sorry, the power. The power of 6 changes from 3 to 4 to 5 to 6. So the power of 6 is changing on this side, and the subscript is changing on this side. So the question is, what's the relationship between the subscript and the power? And if you look at it, in each case, you'll see that the power is 1 less than the subscript. So our guess might be that a sub n is just 5 over 6 to the n minus 1. So a sub n is always 5 over power of 6, but the power of 6 is 1 less than the subscript. That's actually the answer to C. So we've been able to do A and C. The one we don't have yet is B, which asks us to find a recurrence relation that generates the sequence. A recurrence relation, remember, is a way of expressing how one term is related to a previous term. So recurrence relations always have this form where we're asking about a term in terms of previous terms in the sequence. And that is just what's the pattern from one of these to the next. So to go from here to here, here, and so on. Well, the thing that you're doing to go from here to here is multiplying by a sixth. So if you multiply times 1/6, any time you're going to get to the next power of 6. So multiplying by 1/6 at every step takes you from one term to the other. And so if I write a sub n plus 1 is 1/6 of a sub n, that captures that pattern. That, along with the fact that a sub 1 is 5, is enough to generate the sequence. Finally, we have a problem where we're trying to find just a few terms using a calculator. It asks us for a table of at least 10 terms. And I would just use a spreadsheet if it was me, because it holds all 10 terms at once. It's easier to look at. Let me do that real quick, and I'll put a copy of what my spreadsheet shows into the video here. There's a table on the left that shows what a sub n is for each value of n. And again, all I'm doing is putting 1 into this formula, calculating, 2 into this formula, and calculating. So I'm just doing that. I'm doing it in a spreadsheet because I can do it all as one formula. And then while I was in the spreadsheet, I thought, well, I might as well graph it. So I asked the spreadsheet to draw this graph with this is my x's and these are my y's. So this is what it looks like. And so we can see as the n's getting bigger, going 15, 20, 25, the values up here are getting closer and closer to 8. And that's what it kind of looks like through here. So if I had to guess, I would guess that the possible value for the limit looks like it's going to be 8. It certainly doesn't look like it's going to just keep going and going and going.